How's it going, everyone? Welcome, Eulero Gonzalez here, and as you can see, it is way early in the morning, 7 a.m. And in today's video, we're going to look at quick recap of immutability and how do we get here, and then move on to the recursion. So far, what we have looked at is all of this particular concept. So an introduction of the functional programming and why we need to use functional programming and depend on the use case, all right? Because at some point we need to actually build applications that give us high level of confidence when we write them. So with functional programming, the value proposition of this is that the code is provable. So we can focus our attentions is to things that we don't have that high level of confidence, which is usually the business logic that is constantly changed, and therefore other areas where we apply now the functional principles, we can make sure that they work as expected. And it all starts with the definition between functions, purity, and procedures. So the TLDR of all of this, especially on function purity, is that a function must take inputs and outputs. It's also important the relationship between the input and the computed output, as well as the that it must be direct inputs and direct outputs. But we also looked at there is no need to be, it can be indirect input, but as long as they are not modifiers, as long as you don't reassign that. Because when you do, you now lose all of the benefit of the function purity or this particular tools of making your functions pure by following this set of rules. So and also in additional that our function must return is this, given the same input must give you the same output. So with function purity here, we look at what are the things that we need, what are the set of rules that we need to put in place to give the confidence that when we apply this, when we write these functions, or also at function call, because this is the entire reason of this, we can make sure that the function will behave as expected. So by avoiding side effects as much as possible in your function, which is anything that actually modify the state of your application, and it can be network call, database query, or anything that generates CPU hit or CPU time delayed. So for example, timestamp or random generation numbers. So for those cases, we have now techniques to deal with that. So for example, if a function now is going to run some arbitrary code, or is going to now perform some side effects, all right? One of the techniques is that you can encapsulate that in a function, take a snapshot of everything, and then restore the state afterwards. So this is one of the techniques of extracting the impurity of function call. The other is when you need to is write a function at the definition time by taking the lexical scope and then return a new state out of this. So this is all about function purity. We described briefly the arguments adapter and the point tree, especially this, because functional programmers are obsessed with the shape of the function, and they call this as the function signature. And the function shape is just the number, the type, and the order of arguments a function receives, and the number, the type and the order of the shape or the argument that a function uh, that come out of this function. So this is similar like Lego pieces, when you have different Lego pieces and then you want to stack each other to see how they fit together, which is a great stuff. And they are quite obsessed with that, especially how they can shape or how they can change the shape of these functions, whether it's unary functions or binary functions. Usually we use binary function because this is the most, and I really understand that, the most favorite type of function that functional programmers actually love. And the second favorite one is binary function, that it receives two arguments. And it's important to define is what an argument and a parameter is, even though that they technically use, even though that they are used indistinctively, they're technically different. So argument is the value that you pass when you call a function, and the parameter is the name of the inputs at function definition perspective, right? So with this, and also look at how you can now change the shape of these functions by defining some higher order functions, and then you're going to play with that, right? Also look at the function library approach. The library out there, for example, like Ramda and Lodash. And now that we know how can we change the shape of the function, which is something critical, as well as look at the point-free definition, which is just a fancy way to say, hey, if these two functions has the same shape, we can now apply something known as equational reasoning. So they are equal in shape. So equational reasoning is say, hey, if this function output is the same shape as the function input of another function, right? So now we can is define only in terms of its name. So we don't need to pass the data points or the inputs as they call here. Why this is important? Because the value proposition of point free is that we can clearly see the relationship when we call a function. And this also can be a point when you're starting to decrease the readability of that, and especially if you are not quite familiar with point free. And another topic that is interesting, especially when it comes to the idea of functional programming, where you have now generalization and specialization. When you have now general utility functions, so for example, the model, right? And then you want to now create specialized functions like model 2 and model 3 and model 4. And you create now another general utility functions, for example, like is equal to 1 or is equal. These two numbers that I'm receiving are equal, right? And then you now fix, do this, and then you now fix or create now generalizations. Would say, hey, is this equal to 1? Is this equal to 2? Is this number equal to 3? The idea of this, especially with point free, is that give us this ability that when you combine with stuff like closure, which is just the way how a function close over variables, and closure is just the ability to remember variables that are outside of the functions when they, whenever they were, even though they were called, or in this case, a closure. I think a closure is something quite interesting here to mention. So closure is when a function remembers a variable around it, even when a function is executed elsewhere, right? So why this is important? Why is important to know when a variable is remembered even though that the function is executed elsewhere. Because with closures, it unlocks powerful patterns in the context of functional programming. They are not functional, pure closures, but they can be functionally pure. So the TLDR of closure is that any time that you need to modify is the state of a closure, all right, or a variable that you want to remember, do not mutate that state, and in fact return a new copy of that. So if you're going to use closure in a functional programming, you have to make sure that you're closing over state that won't change, over non-mutating state. And at some point, if you want to modify them, it's preferred to return is that function with this new setup. Why this is important, especially the concept of closure and all that kind of thing, because with closure, it allows or it unlock patterns like the iterators, the generators, as well as the model pattern, which is something that we already have in Script, right? The EX6, when you have now, instead of using CommonJS, when you say model.export, you can just is import or export, and then now JavaScript knows that, hey, this will be a model to import or a model to export, and this will be the properties that I want to export as well, or the property that I want to import, whether it's classes, cons, functions, variables. And with closure, or when you talk about function execution, it is important to know when this function needs to be run, whether it's eagerly, lazy or eagerly execution, because here you can decide when this computation needs to be run. Because sometimes you don't want to run a computation initially, you just want this to wait for that, and then whenever you see fit, run that computation. So for example, you don't want to run is a database query on all of the users that log into your app when they want to search for something, right? So you want this to only allows authorized users or logging users, right? So, but the point of this is that, and once we understand this, okay, in how can we now is explore is the idea of what a function is at the end of the day, especially with memoization, what is the techniques that allows to do that, and why memorize is something that is quite useful, especially because it allows you to keep track, it allows you to store previous computations so you don't need to rerun that again, okay? So for example, we can assume that hooks or this state in React are actually using a memoize for that, to be more direct. So when you use memo or use callback, what is doing behind the scenes is, in the case of React, is say, hey, if this function was if this parameter changed, especially on the use memo, is this property changed? If they're not, I'm not gonna re-render this function. If this function call change, if it is, all right, then I want to actually rerun this function. When you use callback. So the point of this is to know when you want to run your functions, even though that you already have calculated that, and if it is, all right, don't do that. So just give the output, the result, but if not, it's going to compute that, store that in your cache, and then give it back. So the TLDR of all of this is that with function purity, all right, from the caller's point of view, is any time that we now call a function, we can replace it as returning output in any place of the application, and that won't affect the rest of the program. That's what referential transparency means, and it means that at the function call, and that makes a lot of sense, because at the end of the day, that's what you want, certainty, when you are now going to write this kind of application, when you're going to use an application that somebody else wrote that, right? So that's where we look at this generalized and specialized function, a very important topic, especially when you need to look at things like composition, and how by having this helper or these general utility functions that allow you to, by looking at these general utility functions, when you can now take a specialized or slice functions out of that, the whole point of this is to increase the readability in there. And also, it's important here in function parameters to pass the order of the arguments from the most general to the specific one, from left to right. And this generalizations and specializations, it has also techniques similar to the pure functions. When you have now stuff like, hey, this is the technique that allow us to take a snap to define is the function purity at a function definition. All right, so you take now the lexical scope and then return a new state out of that. Or at function call, another technique to extract the impurity is by taking a snapshot of everything and then restore the state afterward. So pretty much like this, this particular technique, specialization technique, partial application and currying. So partial applications, it's I want to apply a predefined set of arguments right now, and the rest later. All right. So for example, here this is the partial. Okay. And the other is currying, which is like a cousin of partial application. And it say, hey, I want to now is transform this function inputs into transform the function inputs to receive is a series of sequence of input, or to receive is a series of inputs, to receive it is input as a sequence of functions, until you now have all of that and transform and do the calculation in function. So this technique is called as currying, because Haskell Curry is a mathematical programmer actually use this particular technique. Most of the time we're going to look is something called the loosely currying, where you're not going to pass this instead of a series of inputs, instead of a series of input unity functions, you can pass this with 2 arguments or more. And I think this is more for convenience. In terms of how you're going to modify is the shape of that particular function. So this is where we look by using is now is that, right? You say curry, and this curry add function, you say, hey, I'm going to transform is the input of this function into now a sequence of input functions unity call, and by the time that is done, all right, now you can actually compute that. So this is an extremely common technique in functional programming, all right? Which to me was like, what? That lands out, or that lead us to the composition. And how composition here can we define in terms of it is declarative data flow? Because at the end of the day, we can now create these wrappers around several different functions that is going to be executed, right? So for example, like a factory here, where you can say, hey, I want to compose this series of functions, or a function that makes another functions, all right? Or a function that creates another functions. And then I want to have all of their return, and then I want to have a return value. So by passing initially is the input, all right? This compose 3, as you can see, is just this higher order function, which is only works for 3 functions, okay? And then you pass now, or when you call the function, you're gonna pass the initial value, and this initial value will be the input of the first function. The return output of the first function will be the input of the second function, and so on and so forth, okay? We can also think of now more general functions like that. So compose is the way of how you can now is pass the input and now pass an input and pass through a different functions until you get the desired output. And this is read in the computer science from right to left. And the pipe is similar, but you're gonna pass this input to a series of transformations, or to a series of functions from left to right. And this is quite interesting, because also we were asked to say, hey, how you can now write is pipe and compose. All right, so we can write now a pipe in terms of that. We know that this is a high order function that is going to take these collections of functions, as you can see here. Okay, we're going to take this a collection of functions. We don't know how long it will be, but we know that when we call that function again, which contains now the argument, the value, all right, we want is to pass now that to the function, and then the return value, we want is to now pass that again. So that's when we define this function here and say, hey, given these collections of functions, the first function that I'm going to receive from these collections, I'm going to pass now the output of this, and that will be now the input for the next function. And then after you pass these inputs to all of this series of transformations, then I want to have now the return value, as you can see here. And this is mind-bending stuff. This is how you can now pass a collection of values with functions, right? So you have now this collection of values with all of this series of functions. And the first function, you're gonna pass the inputs, and the returning output will be now the input again for the next function, right? And here you of course are mutating is the state of the of your function here, or the state of that. So here you of course are mutating is the state of that. But there is no any problem, there is no any issue here, because we are not closing over, we are closing over to functions, but functions won't change. So that's a great stuff. So, but in any case, this is how you can now write is a pipe collections into that. That makes a lot of sense. And the idea here is to understand that how now the input of one function, or the input, Your understanding is the implementation details here. That's what it is in this particular pattern. So this input that we're receiving here, and we're going to pass through these collections of functions, is going to be the input of this function, and the returning output we're going to override that value, or we're going to override that value, which will be the input. All right, and when we call that function again, we want to pass now this new computed input, or the returning value from the function 1, that will be the input to the function 2. The returning output of this function 2 will be now become, so we are rewriting is that with this new value to be now the input of the first or the third function, and so on and so forth. But this is the details of this. And the details are important, especially if you want to implement that, and especially if you want to understand how now pipe works from right to left, and how compose works from left to right. So this gives us now a good sense of how you can now create a utility functions that is going to trigger a series of functions based upon an input. Or in other words, you can think of this composition as an assembly line, just like that. And then we talk about now immutability. So here immutability is in the context of software engineering. It doesn't mean what we think about in plain English, which is something that it won't change. So immutability means is that any change that needs to happen, it doesn't go unaware of us. It doesn't go unaware. So in other words, is that immutability here is now a control mechanism in which, or as a way to describe this more briefly, this immutability, that we can now think of this as value immutability, or assignment immutability, which is at the end of the day the reason why const keyword exists, is to say, hey, this will be is so you won't reassign this immutability, or you won't reassign this value, you won't reassign this variable or this constant, okay? But most of the time, our issue of JavaScript programmers comes when you mutate is the value in it itself. It's not when you reassign that, it's when you change the value of something. So this works well for primitive, right? So number, string. But when you need to work with objects at an array, that's when const doesn't work as expected, because you can actually mutate is the value that are inside of this collection, and JavaScript will say, okay, hold bro. You know, and JavaScript will say, okay, hold bro. So for example, let me show you this. You say const here, and you say so numbers, right? So you have a collection of numbers here: 2, 3, 4, 5, 6, 7, 8, and 9, right? You have this collection, which is good, and then you want to say, hey, numbers, I want to now reassign a value at this position. That'll be now, instead of 1, it'll be 2 in a live view. And this is when the confusion kicks in. So yes, you can train yourself to understand what's going on behind the scenes and yada yada yada, because at the end of the day, JavaScript is saying, hey, I won't allow you to reassign the value of this identifier, but I will allow you to reassign the value of this object. And this is when now this confusion kicks in. And for example, the Java community actually have a keyword called final to say, hey, this will be the final state of your of this label, and you can change, you can reassign them. So why am I making this quick pause here? You know, I'm doing it because when you talk about immutability, what actually causes the most problem is when you reassign the value, when you let the user to, or the author of the code, to reassign a state. And frankly, functional programmers, they don't even care about assignments. They don't assign anything. This is an anti-pattern in the functional programming. So that's what I look at this and say, the problem is not the assignment, the problem is the value. And this is when now, by looking at this particular definition here, all right, that let's say you have now a global state in your JavaScript function model, right? You have now this global state that at some point some obscure function is modifying their value here. So when that happens is when an issue occurs, when the problem is happening, and it is very hard for us to keep track of that. So there are now several techniques that we can use to to inform the author of the code. It can be even your future self, to know what will be the data structure, or what will be is the value of this. All right, so you can use the object.freeze. You're gonna pass now to a function call to indicate to the author, to the reader of the code, hey, this object that you're gonna pass is read only. And this is not only enough, because once you receive that as the function call, you just take a copy of that. So you never mutate is an object, you never mutate is a reference. You only take a copy of that, the read-only data structure, okay, that never needs to mutate. Instead of trying to mutate that, no, you create now a new copy of that, and then you now return is a new copy, or then you pass that to the function that do the side effects. So making a copy of this and change it locally is what is sometimes is useful. But if you can imagine a program that only is read state only and they don't mutate the state, that's a pretty boring and non-useful app, right? Because if that actually can change the state of your application, it's like you're gonna ditch that app quickly. At some point, we need to mutate is the state of our application. That's why when you look at Grady Booch, a fascinating history of software engineering, that the history of software engineering is that one that is the one that is let me put it his word. So the history of software engineer is that one history software. So the history of software engineer here, like this.
So I alluded,
as you mentioned here. So the history of software engineer is the ones of rising level of abstractions.
the entire history of software engineering is one of rising levels of abstraction. So what we're seeing here is the rise of another level of abstractions, which gives us all these extraordinarily powerful frameworks from which I can build systems, and which, as I alluded to, the architectural decisions that were front and center for us back then are now embodied in these. So now becomes a decision: what cloud service do I use? What messaging system do I use? What platform do I use? That's the decision, which has a lot of economic decisions and not just software kinds of decisions associated with it. So I think the role of the architect, in effect, has changed, because now I'm dealing with systemic problems, not just software problems themselves.
Great.
So exactly. So as he mentioned, is kind of like that. And you may wonder, is like, why this even care of this on the functional programming, on the immutability, all that kind of stuff? It's like at some point you need a program that needs to change the state, and when those changes happens, you need to have a mechanism to know what went wrong or what happened. And this is now when the immutable data structure kicks in, because the immutable data structure is the one that controls when and how value change, right? So right now we don't have any native built-in JavaScript that allows to keep track of this. There's some proposal for that, but let me be clear that when you look at a proposal on this technical reference, it's something that can take a decade from now to be applied. So right now we have libraries like Immutable.js or Immer that allow us, in the case of Immer, is using now proxy behind the scenes, which is now a JavaScript objects that give you now, or that allow you to intersect when a property change, and therefore you can now run some code. So in this case, now Immer, especially proxy, allow us is to have that control mechanism. So when an object property change, we can now run a command that notify us that, hey, a change were made, and see how can we do that. So that's why we use, for example, Immer in React for that, as a way to let us know when a state change. So this library actually now is keep tracking of our state in React, which to me is something cool, by the way. And now, and then we also look at this immutable exercise here. I don't know if I made that. The immutable. What about this? Yes, immutability here. Okay. Exactly, immutability solution here. So the thing here of this immutability is that anytime that you need to run, anytime that you, from the function definition, you need to create a new state, and if you find yourself calling that function, or calling a calling a function that runs a side effect, instead of calling that inside of your functions, you're gonna call this at the function call, which means that you already have the computed value, you receive the computed value, and then you can now recreate or do the new copy with this new state of that, which is exactly what we did indeed here, right? So I think that this was quite interesting an exercise, because now we have, from the function call perspective, we know that this function won't mutate the state of our application, because we're saying, hey, I want you to compute this lottery number, which is now a side effect generating some random numbers. Once you get that, and then you're going to pass now this object. You tell the user, hey, this is a read-only function, all right? And by the time that you call this, you're now returning is a new copy of this. And this is when the mutations can happen. So this is quite powerful. This is very, very quite powerful here. Very, very quite powerful. So anytime that you call this function, what you're gonna do is to record a number. A new number that is passing here, a new number that is passing here, a new number that is passing here. So record number is a lottery num, and I'm gonna use to store that in here, to lucky lottery numbers here. And again, remember that we are now passing is our arguments from the general to more specific one. So we call here is a function, and then also the specific data, which is in our case a collection. So slowly but progressively, things started to make a lot of sense. A lot of sense.
For the day. If any of you go win $1 billion, I expect 10% of it, okay? I know when I...
So now let's go to what we really care in today's video about the recursion. All right, let's get into this.
Bring up that word, recursion. It sends shudders through the spine of many of you because you're thinking, it's so difficult and so complicated. And I want to assuage those fears. I want to allay those fears and tell you that recursion is not as complicated as it's often made out to be. I remember distinctly when I was back in school, who knows how many years ago, I remember feeling frustrated and confused by this topic, but I think it's more related to our lack of proper perspective on the topic than the fact that it is just inherently hard to understand. And as a functional programmer, as somebody who aspires to use functional techniques, your toolbox would be incomplete if you were to say, no, I'm just not ever going to use recursion. It is a significantly important tool, so we should spend a significant amount of time making sure that we can get comfortable with this topic. Let's take this example of wanting to count the number of vowels in a string. I've got the quick brown fox jumps over the lazy dog. I don't even understand. That's a weird thing from the days of typewriters, because that's a sentence that has all of the letters in the alphabet in it, and that's why that sentence exists. But you know, it's just the first thing that came up on a weird thing from the days of typewriters, because that number of vowels in a string. I've got the quick brown fox jumps over the lazy dog. I don't even understand. That's a weird thing from the days of typewriters, because that's a sentence that has.
Okay, that's a sentence that has all of the letters in the alphabet.
The letters in the alphabet in it. And that's why that sentence exists.
The quick brown.
You know, it's just the first thing.
The quick brown fox jumps over the lazy dog.
Came up on a Google search. So there you go. There's a sentence, and we want to count how many vowels exist in that sentence. And you can imagine very straightforwardly an iterative approach, which is what I'm doing on lines 5 through 13. I'm setting up a counter, I'm doing a loop over that, and I'm checking to see if it's one of those 5 letters that is a vowel, and if so, incrementing my counter, and then returning the number. And indeed, the answer is 11. The problem with this looping approach is that the looping approach is basically telling us you have to read the code to convince yourself of what it does. You cannot simply glance at any given for loop somewhere and absolutely know what that for loop is going to do. You have to read it and execute it. To the extent that it's written pretty simply, it doesn't take a lot of mental processing power, but you cannot glance at this and immediately know what it's doing. So this is one of those situations where we might ask, is there some more declarative approach? And there are multiple ways to solve this problem. I am not suggesting that recursion is the only way to do so. But recursion is going to be a significant solution, or an important solution, that we should get more comfortable with, because there will be some problems where recursion is much more of the best answer to the problem, and in fact, some cases, almost the only practical answer to the problem at hand. So some problems can be solved with recursion, and some problems really must be solved with recursion. And because that is the case, it should be a tool that we are at least familiar with. The question you have to ask yourself is, what would be a recursive definition for any problem? You have to understand a recursive definition for a solution before you can start writing a recursive function for it. I know this is a shock, but as a programmer, your job is not to get the code to work. Your job is to actually first understand the problem. So the real question here is, if my problem that I need, or the algorithm that I want to design, the solution that I want to provide, is how many vowels are in a string, I have to ask myself, how would I define that in a recursive way before I could ever start writing a recursive function? And there are, in fact, often multiple ways to recursively define a problem. Some problems, basically, there's only one. Some problems, there's 2 or 3. So I'm not suggesting this is the only way to approach it, but I think it might be one of the most natural ways to approach it. And it goes under the general heading of reducing the problem set. Okay? So I have an undetermined number of characters. I don't know how many characters are in that string. I have an undetermined number of characters. And in fact, if I'm trying to create a utility for this, it needs to handle any string length, from 0 all the way up to infinite string length, right? So I don't know how many characters I might have to look at. But what I can say is that it would be better if I solved a smaller problem. Whatever the string length is, if I was looking at one fewer character in that string, that would be an easier problem to solve than my current length, by 1 character. And if I can think of it as reducing it by 1 character, then I can think about doing that again, and now I've reduced by another character, and doing that again, and now I've reduced by another character, and so on. And so we can, from that way of thinking, by saying I want to reduce my problem set to something that is easier to solve, from that way of thinking we can say the number of vowels in this string can be defined as the number of vowels in the first character plus the number of vowels in the rest of the string. Now, number of vowels in the first character sounds like a silly question to ask, but it's basically just a binary choice. Is a vowel or not? So it's a 0 or 1 sort of question. And whatever that number is, plus however many vowels are left in the string. And then I could repeat that process by saying I've got a smaller string, and I could say, how many vowels are in that one? As a matter of fact, I could do that exact thing that I just described iteratively. You could set up a for loop that looked at the first character, said if it was a vowel or not, added 0 or 1 to the count, and then reduced the string size. As a matter of fact, that's sort of what we're doing with the index here. We're sort of indexing through the string rather than trimming the string down. But we're saying, how many vowels are here, plus how many vowels do I need to count in the rest of the string? That's the recursive, or a recursive way of thinking about the problem. So let's try to set out to design a recursive function that solves this problem. Every single recursive solution is going to have, at a minimum, a base condition. The base condition is how you know when to stop. It's just like in a for loop where you have a test condition that tells the for loop to stop so you don't get an infinite loop. In our case, the base condition most naturally is I have an empty string. Because if I have an empty string, I can definitely tell you there are 0 vowels in the empty string. So that's what I'm checking on line 2. I'm saying if string.length equals 0, just return 0. That is a base condition. And then I need to ask, what do I do if it's not 0? Well, I need to count whether or not the current character is a vowel, and then I need to count all the vowels in the rest of the string. You with me? So how do we do that? First, line 3, create first, and we set it to 1 or 0. If string sub 0 is a vowel, we set it to 1. Otherwise, we set it to 0. And then line 4, we take whatever that value was, and we add it to the count of the vowels in the rest of the string. String.slice with 1 says slice off the first character and give me the substring that's left. So make it a smaller problem. Smaller and smaller and smaller problem. So if we started out with a string that was 100 characters, the next time we called it, we'd be at 99, and then at 98, and at 97, and all the way down until we got to a string length of 0, in which case we'd get 0. Now we'd have all those stacked up 1s and 0s, 1s and 0s, 1s and 0s, and they're all in a big, giant, basically addition string. 0 plus 0 plus 1 plus 1 plus 1 plus 1 plus 0 plus 0. And we just need to compute all of that. And that's what the return statements are going to do, and they're going to give us back the number, in this case the number 11. Now here's why I think recursion gets confusing for people. I think recursion gets confusing for people because they force themselves to try to think about the implementation of what's happening with recursion. The same way they think about the implementation when they write the for loop. And this is where we get off track, because recursion is not designed to be an imperative approach. It's conceived to be a declarative approach. Remember, declarative says, I'm not concerned with how it happens. I'm concerned with the outcome. So if I can say, in my mind, that I understand the idea that you could count all of the strings, all of the vowels to the right of me. I don't know how you're going to do it, but I understand that you could theoretically do that. And I can understand the problem of whether or not this single character is a vowel. And I can understand the idea that those two things add together to give me a total count. Then I do not need to concern myself with how that other sub-problem gets solved. You can, if you want to be a computer scientist, start drawing all these diagrams of the stack frames and the function call and what the values are. But I think that's where people get off track. It's not that I don't want you to understand that stuff, but that's really deeper, like, that's like computer science level kinds of stuff where you need to track all the memory frames and all that stuff. What I want you to think about as a functional programmer is, can I break this problem into some pieces that are easy to understand? I understand that character 1 is either a vowel or not, and I understand that there is some way to compute how many vowels are left in the other string. And I'm going to add those two together and give you your result. And that's as far as we really should have to go in terms of conceiving and authoring our recursive algorithms. If you find yourself having to go deeper than that, then recursion might not be the solution that is best for you. Hopefully, that idea will resolve some of the frustration that you may have built up in the past about recursion being confusing to author, confusing to understand. And the point that I want to make here is that even though there is some degree of imperativeness in this code is much less imperative than the iterative equivalent on the previous screen. If you get to the point where you start to understand the patterns that happen with recursion, and there are a couple of major patterns that almost all recursion fits into. One of them is solve the subproblems. That's the one I just talked about. Do something and reduce my problem set to a subproblem and keep reducing. Another one's called divide and conquer, which takes a giant problem set and says, can I eliminate half of the problem? And then can I eliminate another half of the problem and another half of the problem? That's another pattern for it. If you can get to the point where you understand those patterns, then you will start to be able to see a recursive problem like this and say, oh, I know exactly how they're solving it. They're solving it with the iterative subproblem. They're solving it with divide and conquer, etc. Okay? And there's a tremendous amount of math behind that, and none of that math even matters. All that matters is that we can trust that that stuff works. You don't have to be able to write the inductive proof for this thing. You just have to be able to intuit that I understand that this part of the problem could be solved, and this part of the problem I can concretely solve, and now I'm done.
I concretely solve this part. I already
Now, there's
solved
one
the
little
problem?
part of this particular
I'm going
recursive
to
algorithm that I'll
solve
call
what
out.
is
This is
good.
sort of a little nuance, but it actually can sometimes lead to better solutions. So I want to at least call this out. I know when I bring up a point where you understand those patterns, then you will start to be able to see a recursive problem like this and say, oh, I know exactly how they're solving it. They're solving it with the iterative subproblem. They're solving it with divide and conquer, etc. Okay? And there's a tremendous amount of math behind that, and none of that math even matters. All that matters is that we can trust that that stuff works. You don't have to be able to write the inductive proof for this thing. You just have to be able to intuit that I understand that this part of the problem could be solved, and this part of the problem I can concretely solve, and now I'm done. Now, there's one little part of this particular recursive algorithm.
This part of the problem.
Now, there's one little part. I know when I bring concretely solve.
Exactly. This part of the
this
problem.
part of the problem, like
so,
proof for this thing. You just have to be able to intuit that I understand that this part of the problem could be solved.
This part of the problem could be solved, and this part of the problem I concretely solve. So I already solved this, and this part of the problem it could be solved.
And this part of the problem I can concretely solve, and now I'm done. Now, there's one little part of this particular recursive algorithm that I want to call out. This is sort of a little nuance, but it actually can sometimes lead to better solutions. So I want to at least call this out. It's one thing that's always kind of bugged me about recursive solutions. The base condition here is at that very last time. Remember, we've got a string that's 100 characters long, and we pass in that final empty string. We make a function call. We pass in an empty string just so that we get 0 back out. What has annoyed me always is that always felt like a completely wasted function call. Like, if I could just look ahead one character, I could know that I don't need to make that final function call in that particular case. It's not that that final function call is the difference between a performance solution and not. Okay, so I'm not making a performance question here. This is more of almost like an obsessive kind of thing, like, no, I don't want any more function calls than I ought to have. I want to design an algorithm that only does the bare minimum necessary function calls. So is there some way for us to preserve the declarativeness of this, but still avoid that final base condition? And this is the pattern. It's a slight tweak on this pattern that I want you to consider. Instead of checking our base condition first, we can reorient ourselves to simply checking everything on this first character and only doing the recursion if there's actually more work to do. It's not as complex as that may sound. So let's take a look. Here I'm going to compute first variable. That first variable, I'm going to compute it first. And then my base condition is going to look different. My base condition is going to check for string length less than or equal to 1 rather than for 0. Because I've already computed for a single character string, I've already computed my 0 or my 1. And now I'm simply saying, I only need to do more work if there's actually other stuff in the string. If I'm in an empty string or a single character string, there is no more work to do. So let's not even make the recursive call in that case, simply return the 0 or the 1. And if we've passed that return statement on line 3, we know there is more work to do, and we simply do the same work we did before, which is first plus the rest of the string, the count of the rest of the string. It's just a slight tweak on the way of thinking, but it says do the work now, think about the work now, and then decide if there's any more work to do, rather than sort of thinking about it in terms of deferring the work until later. It just changes the position of the base condition. And I've often found that that little tweak, even though it's sort of servicing my obsessiveness of like not doing extra function calls, actually that little tweak sometimes unlocks better optimizations for recursion. So it's something to keep in your mind. It's something to make sure you're aware of. Okay, let's try out an exercise to practice this whole idea of recursion. In this exercise, you're going to be writing a palindrome checker. If you don't know what palindromes are, this is one of those like classic interview questions. A palindrome is a string that reads exactly the same forwards and backwards. So for example, A, B, C, B, A. If you reverse that, it's still going to say A, B, C, B, A. Okay? So that is a palindrome. There's a couple of base cases, by the way. An empty string is a palindrome, and a single character is also a palindrome, because it reads in both directions. Also, we should point out that both the string ABA and the string ABBA, both of those are palindromes, because in both cases they read the same backwards and forwards. Okay? Now, there's a very straightforward way of solving this problem iteratively. And there's a good chance on some interview question somewhere that somebody's going to have asked you, implement it iteratively. But because we're talking about recursion, we want to move beyond the iterative approach, where we just simply go through all of the characters one at a time. We want to move beyond the iterative approach and try to think about it recursively. I'm not going to tell you exactly how to do it, but there is a hint here that points at exactly the right way to think about palindromes in a recursive sense. So I want you to make sure you read that hint as you tackle this exercise. If you look in the exercise, there's an isPalindrome function that you need to fill out the definition of. It should be recursive. And also, there's a set of test cases down here at the bottom, and all of these should end up printing out true. So make sure you test your isPalindrome function. So I want you to make sure you read that hint. I'm not going to...
Hint, consider A, B, C, D, C, B, A handy recursion definition for a palindrome. If that's the first and last character of the string, the A must be the same character, and the substring in between must be also a palindrome. So I have a problem that I could solve, and a sub-problem that I could solve, and then the problem that I solve. So I'm looking at the last one here. So this is the problem that I solve, and there is the problem that I could solve. And I'm gonna pass now a string version of this, a string version of this, a string version of this, a string version of this. So if that string version that I'm passing here is now one or zero, okay, if that is 1 or 0, then I want to compute that. So how do I compute that? So by checking if that the characters at that positions are the same. So by solving this problem and this problem, and if they are the same, now I'm going to exactly. If they are the same, if they are not the same, that will be my stop condition. If they're not the same, they're not. It's false. So return false. If they are the same, now I want you to call this.
I'll tell you exactly how to do it, but there is a hint here that points at exactly the right way to.
So based on your approach of doing this kind of stuff, right? So if I have now a palindrome, oh my God, no. If I have a palindrome, if I have this palindrome, where I say A, B, C, D, and C, D, and C, B, A, if I have this palindrome, which is the palindrome, say cons palindrome, right? That will be is now a string, okay? A, B, C, D, D, C, B, A, that's right, a palindrome. And then I define a function to know the palindrome is palindrome, okay? To compute that, I'm going to receive that string in a recursive way and say, I need to define my base condition, my stop condition here. That'll be is if the problem that I'm solve, so the problem that I could solve and the problem that I solve, okay? So the problem that I solve is that if I take these two, if the first element, okay, so I need to verify if that is string, I need to verify is that a string, okay, is that a string dot length is equal to 1, all right? So if that is 1, all right, so if that is 1, meaning if you're receiving is 1, you're gonna pass is true, right? So you're gonna return is true. However, this is when now I need to compute this. So if the string is more than that, so this is where I need to compute this. And what I'm going to compute is the first element. So if the first element and the last elements are now the same, good, move on, all right? And let's going to call this palindrome without those block. So without the first and the second. And let's go to compute that if this is length is 1. If it is, return true. And so on and so forth, right? So what you're doing is trying to decompose all of this in this particular sequence. So here you have now the first element, which is string at the first position, all right? Or you can say it's now something like this. First element and the second element, right, which is the string at that position, string dot length -1, because the way how now you allocate memory start from 0, okay? And then you say, hey, I want to return is the first element, is this first and the second element the same? So I want you to return is now this, all right? In palindrome, all right, I already compute this, and I'm going to compute the next one, which is Let me put it here now, the new sentence. That will have is now the you say string dot slice, I think it is. You say string dot on shift, so remove the element from that. All right. Oh, because it's on shift. I'll remove the first. Is shift, exactly. Shift. So remove the first one. So remove the first one and the last one. Pop. Right. So if you do something like this, for this case, and then you say, hey, this will be now the palindrome. And then you say, hey, this palindrome will be shift, and this one. Palindrome shift is not a function. Really? Oh, because it is. Okay. It's because it is. It's a substring. So you can say, give me is the substring of this. Yep, much better. You can say is the substring, in this case, will be much better like this. So substring of the palindrome of the first position, right? Okay, good, good, good. Exactly. But it takes the first element and the second element. And we want is what is left. You know? We want is what is left. Mm-hmm. Mm-hmm. Returns a new length. Mm-hmm. Returns a new length. Mm-hmm. Okay. So, well, what we can do here is to say splice from this index to another index. Mm-hmm. Mm-hmm. Okay. Okay, I need to work with strings, bro. Okay. Okay. Mm-hmm. Entry adds field filter, fine. Mm-hmm. Path end, path start, repeat, replace all, search, slide, split, substring. To uppercase, to well form. Slice. Okay, so what can I say here is say something like this. Slice. Okay, slice that first element. All right. to palindrome dot length -1. It is this one. And then the next one, since the palindrome that we're going to pass is this, it is now different. You say, hey, count palindrome 2, which is here, and if we say this one is now this, and this, and this, exactly, but it's with slice. It is with slice. So here we can say, hey, I want to slice, I want to say string dot slice 1, 2, like this, string dot slice length -1, and this is what we're going to pass now to our new function. And this is the problem that we could solve, is palindrome with the new sentence. So if we call here is palindrome of this word, we say palindrome, and now it gives us true. Holy shit, bro. God damn. And if you pass, for example, another palindrome, is palindrome of this, it will say, of course, this is now true. Exactly. B, of course, false. C, and they say B and C, A, you know, and if you pass now a D, C, it's funny because it's actually computing at this moment. So this is a way of how you can solve now this palindrome here by solving is, or by having this problem that you could solve, but you and this subset of problem that you solve here. Holy moly, bro.
Think about palindromes in a recursive sense, and all cases. Okay, let's talk about the solution to the recursion exercise. If it helps, you might have wanted to try it iteratively first, just to wrap your head around it, but the hint in the README really was designed to help you skip right to thinking about the is palindrome. As we said in the lecture just a little while ago, there are various different strategies for solving things recursively, and one of those strategies, a very common strategy, is solve the subproblem. Reduce the problem set by one or more and solve the subproblem. So that's what's hinted at here, is that the question of if an arbitrarily long string is a palindrome can be formulated recursively as, it is a palindrome if both of these things are true. Number one, the first and the last letter of any given string have to be equal, and everything in between has to be a palindrome. So if you think about this string, the A, B, C, D, B, A.
You already give me the hints.
The
there.
A and the A are equal. And if we look only at B, C, D, B, that is also a palindrome. So the recursive definition for a palindrome is that the first and the last letter are equal, and everything in between is also a palindrome. And of course, you answer that by doing the exact same thing, comparing the B and the B, and everything in between is a palindrome. So that hints at how we would approach the recursive solution. Let's take in a string for our is palindrome, and let's consider our base condition. How do we know what our base conditions are? Well, I hinted at those here. I said both an empty string and a single character string are in fact palindromes. Just by definition, they are palindromes. So if string.length is less than or equal to 1, then we know we have a palindrome. That's a base condition. Now, if we are in a length that is 2 or greater, then we know we need to do some comparison of characters. So if we are, so the way to look at those characters, we'll set up the first variable, we'll look at string sub 0, and the last variable we'll look at string
is the problem
of string.length minus 1.
Exactly.
We'll access the first and the last character. And we need to check to make sure that those are equal. So if those two are equal, if first equals last, then we know we have more work to do. But if first doesn't equal last, then we definitely don't have a palindrome.
Don't
So
have
we
a
return
palindrome.
false. If the first does equal last, then we want to solve the sub-problem, which is the stuff in between, is that a palindrome? Even if there's nothing in between, we still have that question of, is it a palindrome? So we can simply call is palindrome
with now
with a substring.
this not
String
substring.
dot substring, and that takes in two indices. We want the substring from position 1 to the position non-inclusive of string.length minus 1. Checking the documentation on substring in all languages that there's a substring. It always
We use now the string slice with that, or substring as well.
goes non-inclusive to the final index. So that's why we say minus 1 instead of minus 2 there. So this is going to get that smaller substring, which in the case in the README would have been the BCDBA, the BCDB. It's going to get that substring, and it's going to ask, is that a palindrome? And then so on and so on.
Why is that not the 1 after the substring? The 1. Why is that not a 0? Wouldn't you want?
We want, because it's inclusive on the left-hand side and non-inclusive on the right-hand side. We want to start at position 1, not at position 0. We've already looked at position 0.
Okay.
So remember, we've trimmed off 2 characters here. We've trimmed off this character and this character, and we want to look at everything in between.
But it still knows that spot is 1, even though you've trimmed.
We didn't change the string yet.
Okay.
We just looked at it. We said string sub 0.
Okay.
And then substring is actually getting a subset of this character. Still not modifying the string. Remember, a string is immutable. It's not going to change. So we'll just do a quick check to make sure I didn't make a mistake here.
In my case, exactly. You're just creating is a new copy of this. So string and not. You're just getting is a new copy of this. So with string slice, exactly, and returns it is a new string without modifying the original string, which is that is the reason why you use a slice here. So we create now a new sentence to check this palindrome new sentence. So in my case, I did this because I want to know, this is the problem that I solve, okay? If that is true, all right, let's go to now check at the next problem that I need to, that could be solved. That's why I look at this.
We'll run this code and we should see all of our test cases pass. And we see them pass. And so we passed the job interview and hopefully got the job. So let's talk about recursion in the practical sense. We can get a sense of the theoretical way that this works. But in the practical sense, many of you probably know that recursion often doesn't make its way into production applications for one particularly sticky reason, which is that range error that we get thrown whenever recursion has been running for too long and we get a range error thrown, Stack Overflow exceeded. Okay? That's the major problem that I think for the last 50 or 60 years has essentially limited the utility of recursion from being a general programming thing that everybody has to learn and everybody has to use, is because a lot of people basically think in the back of their minds that sort of nagging feeling like, yeah, it sounds good in theory, but in practice it would probably blow up, so I'm not going to use it. And so I want to talk about that because there are ways of addressing this problem. In theory, your computer could just run forever and you'd have infinite memory and infinite CPU, but in practice we know that's not the case. And so we do need to actually step in. A little bit ago I said, try not to think too much from a computer science-y perspective about what's happening in memory. But to get an intuition for why there is a practical limitation problem, we do need to think just a little bit about the implementation side of it. Okay? I don't want you to think about implementation as you're authoring this code, but it's just to get us a sense of the problem of the range error, of the Stack Overflow problem. So if we think about when a function gets called, when one function is running and it calls off to another function, it doesn't have to be its own function, it doesn't have to be recursion. It's just the general problem that when one function calls out to another function, at that moment, everything that was currently happening in that function needs to get saved somehow so that all the stuff that happens in the other function doesn't mess up what was happening in the first one. So if you're in the middle of function A and you call off to function B, you kind of have to have somewhere where all of A's in progress work is saved so that there's some place, a scratch pad, if you will, for the work for B to happen. And in computer science terms, we call these stack frames. Every time a function gets executed, an area of memory is reserved, and it's called a stack frame. And we call it a stack frame. We actually call it a memory frame. We call it a stack frame because when one function calls another, and then that one calls another, and that one calls another, what we have is a stack that's growing. You have at the bottom level the initial function that called off to B, and B called off to C, and C called off to D. You're building up a stack. And we use the stack data structure idea because when this this topmost function, if you will, finishes running, and its work is done, we can get rid of that memory, and we pop the stack back to the previous one, and it picks up where it left off, and then we pop the stack back to the previous one. And it might call another and another and keep coming back. So we have this stack data structure. Whether or not the computer actually uses a stack, conceptually, it uses a stack to manage all of the work as it builds up and goes back down and builds up and goes back down. So what kinds of things are in these stack frames? Well, you have all of the local variables that have been assigned, any memory that's being assigned for those. You have the program counter, which is basically what line of code it's on or what part of an expression it's on or something like that. So basic things like that, very low-level things that the computer needs to track what's happening inside of a function. And it doesn't take up a lot of memory. We're not talking about like megabytes worth of memory. The stack frame is probably like a few hundred bytes or a K or something. It's probably like a couple hundred bytes at most for each stack frame. And if you're calling 100 functions in a chain, which almost never happens, by the way, probably at the most you probably go 5, 10, maybe 15 deep. But if you've called even 100 of those functions and you've still only used up a fraction of a megabyte of memory, it's not a big deal. You never see any sort of a problem with that. But as soon as we get into programming practices like recursion, it becomes dramatically more likely that that stack frame depth might grow to thousands, tens of thousands, hundreds of thousands, millions, and even beyond. And that does start to chew up some non-trivial amount of memory. Now, this is not a new thought. This is not a new occurrence. Almost the day that recursion was invented back in the whatever 60s, the very next day somebody thought, oh, we only have like 4K of RAM on this computer. We can't do very many function calls in 4K of RAM, right? So back then they had much more of a pronounced limitation than we even do with our fancy gigabytes worth of memory. They had way less memory. So this was a very present problem for them. The math predicted that recursion was this great way of doing things, but in practice we're limited by the amount of memory that we can run. So they immediately had to confront, is recursion something that should just be filed away as a nice great theory but not something that can be used, or is there some way to address it? And the way to address it that they invented back then and has been this time-honored approach ever since is an optimization called tail calls. To understand what a tail call is and how a tail call works, we need to understand when we make this recursive call here, the call on line 4, we need to understand why the stack frame that is currently executing needs to be kept. What is it about that stack frame that still needs to be kept around? And in particular, the reason why that stack frame needs to be kept is because we are doing that first addition, the addition of the return result, after the function completes. So it's essentially that part of the program that's requiring our current stack frame to be around. But if there was no more work to do, if we literally just said return count vowels, and there was nothing before or after that, it just called the function and it was done, then we could think, at least in theory, that it seems like the current stack frame isn't needed anymore. We've done all of our work in our current stack frame, and we're going to dispatch to another function call, and so why don't we just maybe throw away the current stack frame, or just reuse the existing stack frame for the next function call? You follow me? That's the idea here behind tail calls. If a function call happens in a position which is referred to as a tail call, meaning it's at the tail of the execution logic, it's at the very end of that function's logic, then we don't need the existing stack frame anymore, and we can essentially dispatch to another function call and not take up any extra net memory. Which means that function A can call B, can call C, can call D. If all of those calls happen in a tail position, then we've only ever needed one stack frame in memory at any given time. We don't have this runaway of O of n memory usage where every function call has taken up a new section of memory. And it's an implementation detail whether we create a new one and throw the old one away or whether we reuse. It's different under different situations. But the general idea is at any given time you should basically only need one stack frame. That only holds for function calls that have happened in a tail position. Now this is an optimization in the bigger sense of optimization. It's not actually a performance optimization. It's not actually faster. In some cases it might actually be slower to do what we're talking about. So when people say optimization, they usually jump to thinking, oh, well, this is a performance, it's going to go faster. It's not necessarily going to go faster, and in some particular cases might actually go slower. But it's an optimization in the bigger sense because we're optimizing memory usage. We're saying, let's not have runaway memory usage unnecessarily. Let's not keep all those stack frames that aren't needed anyway. Let's run in essentially fixed memory space, O of 1 memory usage instead of O of n. Okay? And it's important to understand that tail calls are an additional feature that the system, your language, your compiler, your runtime has to support. It's not, you don't get it for free. So you would wonder then, well, what about JavaScript? Does JavaScript have this? And for literally decades, people have been calling for JavaScript to have this tail call support, this memory optimization, so that recursion doesn't need to throw this error that says range error out of memory. And by the way, a little side note on the range error issue, that range error, stack overflow exceeded or whatever, that error is there not because you ran out of memory. A lot of people think that's what's happening. It's not an out of memory error. If you have ever had an out of memory condition in a web app, I guarantee you that what you saw was, at a minimum, the browser crashed. And if it wasn't the browser that crashed, the whole device crashed. Anybody ever had your mobile phone just like shut itself off and restart? And you're like, how is that even possible to just be like clicking around on Facebook and all of a sudden my phone restarts itself? Congratulations, that was an out of memory error. Almost certainly, that's what happens when the system completely runs out of memory, just throws its hands in the air and says start over, right? Just restart the device because I'm completely out of memory. And JavaScript knows that that's a really terrible idea to allow JavaScript programs to run a device out of memory, because it's a very clear sort of denial of service attack vector for somebody to run some infinite loop on a page and kill people's devices, okay? So, because we know that's a terrible idea, JavaScript essentially from the beginning has had a check in place that has said, let's not run so far that we are going to definitely eventually run out of memory. And that heuristic, that decision metric for how does it know if it's going to run out of memory, is more complex than you might have expected. It used to be really, really simple. So this is actually true. Back in IE6, there was a fixed limit for the number of function calls that could happen, and that limit was in succession. This doesn't mean total functions ever executed. It means in a chain, where one is called the other. The total stack depth was limited to 13. I don't have any idea where they came up with that number, but if you ever had a situation where you called to that 14th call in a chain of function calls, you would get the range error in IE6. Somehow, some way, they thought 13, maybe they had a heuristic that said nobody ever goes over 13, and if they do, it's almost always recursion. I don't know. But anyway, it was limited to 13, which is ridiculous, right? That's ridiculously low, because that's like probably less than 100K of memory, way probably less than 100K of memory. So, how many function calls should it allow? This is sort of a weird kind of a prediction because it's essentially...
So, that'll be all for this video. Take care. Bye-bye.